Welcome back, everyone. This is the 21st lecture of the condensed matter course. When we left off last time, we were talking about magnetism, and in particular, we were talking about ferromagnetism. Ferromagnetism. And everything that we said about magnetism was really focused on understanding what happens at zero temperature, all of the moments aligning with each other. But generally, you can ask the question, what happens to a ferromagnet as you raise the temperature? And we have a little bit of an intuition about what happens in ferromagnetism at finite T, which will be the subject of much of today's lecture. At zero temperature, all the moments align. But then when you turn on the temperature, there's going to be some thermal fluctuations, and the moments won't be completely aligned anymore. And at some point, we might not have ferromagnetism at all. So in general, what we want to know is we'd like to know, as a function of temperature, what is the magnetization, some sort of equation of state, and maybe we'll also allow for an externally applied magnetic field. So this is what we're interested in finding out. Now, I should start with a bit of a caveat. In the last lecture, we spent a lot of time thinking about the idea of magnetic domains, which are created due to long-range dipolar interactions. And even though the local physics is to align all the moments in a ferromagnet at low temperature, there will be some global physics which will make some regions point up and some regions point down to minimize the global magnetic energy. So we're not going to think about that kind of physics today. We're only going to think sort of locally. So for us, a ferromagnet at zero temperature would have all their moments aligned, at least for the purpose of today, and then we can put back in the long-range dipolar interactions later if we're interested. So we're going to use a very simple model to try to understand what happens to the magnetization at finite temperature. We use the spin 1/2 Ising model. 1/2 Ising. By spin 1/2 Ising, what we mean is that the spin on each site will be some sigma I pointing the z direction, where sigma I equals plus or minus 1/2. And we'll write the Hamiltonian, which we've seen before. There will be a coupling to the external magnetic field, B sum over all sites sigma I. And here I've put the external magnetic field in the z direction. And then we have the coupling between neighbor spins, minus 1/2 j, sum over neighboring spins I and j, sigma I, sigma j. So again, the bracket notation means that I and j are neighbors. And here we're concerned with a ferromagnet, so we said j greater than 0. All right? So this is the Ising model, a fairly simple model to write down, but as I mentioned before, it's actually quite difficult to solve. It is solvable in one dimension. In two dimensions, it's solvable without the magnetic field, and beyond that, it's not solvable at all. So that means we're going to have to resort to some sort of approximation method to get some sort of understanding of what happens to the magnetization in the Ising model at finite temperature. Now, there's lots of approximation methods one can use, but the first resort of theorists, or first resort of scoundrels, is what's known as mean field theory. Mean field theory, which we're going to use to try to estimate what happens to this Hamiltonian at finite temperature. So mean field theory can be approximately defined as whenever you approximate some operator or quantity, some operator or quantity with an expectation, with an average or a mean. And this is used very, very commonly, not only in condensed matter physics, but also outside of condensed matter physics. And this is sort of a very general statement. So there are many things that you can start approximating as an expectation or an average. So we're going to use a particular variety of mean field theory known as molecular field theory. Or also it's known as Weiss mean field theory. Weiss mean field theory, MFT. This is the same guy, Weiss, who discovered the idea of domains in magnets as well. We discussed him last time. And I have to admit, I don't know if it's I before E or E before I there. So I apologize about that. My spelling's not very good. So the idea of molecular field theory, it has basically two very simple steps that you can always follow. Step one is that you should treat one piece of the system exactly. You isolate one little piece of the system. It might be a single unit cell, or it might be just a single site, and you're going to treat that exactly. So treat one piece of system exactly. Treat one piece of system exactly. Everything else should be averaged. All else is averaged. So we've actually seen something like this before. When we studied the Einstein model of the solid, we treated one atom exactly. We treated its quantum mechanics correctly, but we averaged the potential from all the other atoms. We sort of made it into some rough average, and it just became this approximate potential well that that one atom is living in. So even though it was a very crude approximation, that one atom we treated very honestly. It was all the effect of all the neighbors that we approximated. The second step of Weis-mean field theory, step 2, is self-consistency. Self-consistency, which means all pieces should be the same, should look the same in the end. Should look same at the end, in end. So it shouldn't matter which part of the system we focus on to treat exactly. At the end of the day, the whole system should look homogeneous again. Shouldn't be anything special about the one piece we're going to look at. So for us, we're going to treat the Ising ferromagnet, and we're going to focus in on just one site, or one unit cell. In this case, the Ising ferromagnet, the unit cell is a single site. So we focus in. Okay, so step 1. Look at one site. Look at one site. Site I for the Ising ferromagnet. I'll write down the Hamiltonian for site I only. So Hamiltonian for site I is G mu B B times sigma I. That's the coupling to the externally applied magnetic field. Then there's going to be the coupling to all of its neighbors, which I'll write this way. J is neighbor of I. Sigma j, and then times sigma I. So I've written out all the terms in the Hamiltonian that contain the spin sigma I. Right? Now, you may have thought here for a second that I may have dropped the factor of a half that's written up top, but I haven't. Then remember that the factor of a half up top is there because in that sum, strictly speaking, there's sigma 1, sigma 2, but there's also sigma 2, sigma 1. In this sum, if sigma I is sigma 1, it doesn't occur the other way around. It only occurs once. So sigma 2, sigma 1 would just be represented once in this Hamiltonian. So you don't need the factor of half when you write it this way. All right. So this looks a little complicated. Let's see if we can simplify it a little bit. We'll define an effective magnetic field, B effective via the following equation. G mu B, B effective, equals G mu B, the actual magnetic field, B external, plus or minus the influence of the neighbors. J times sum over small j is a neighbor of I sigma j. So what we're doing is we're wrapping up the interaction with the neighbors, and we're calling it part of the effective magnetic field. Okay? In terms of this quantity, we can rewrite the Hamiltonian for site I as just G mu B, B effective times sigma I, which looks extremely simple. It just looks like a single spin, sigma I, coupled to an external effective magnetic field, B effective. And we know how to solve that. We solved that before. We just have a single spin in a magnetic field. It should be easy, right? Well, okay, that's a little deceptive because we've sort of lied here. B effective is not just a number here. It's not a constant. It actually has some degrees of freedom hidden in it. You should think of it as an operator. It has all these sigma j's in it, and that complicates life and is going to make everything really complicated. So we can't really treat this simply as a spin coupled to a constant magnetic field. Okay? So that's where mean field theory comes in handy. The rule of mean field theory is that you should approximate everything except this one spin in terms of an average. So step one is approximate B effective by some average of B effective. Okay? By taking this average, instead of being an operator, it's now just a number. So the Hamiltonian becomes, step 1, the Hamiltonian becomes HI is G mu B, expectation of B effective, which is now just a number, coupled to sigma I. And that really is just a single spin coupled to a constant magnetic field. So we know how to solve this. We've done it before. You've done it last year. We did it in the last lecture. So I'll just write down the first step. You write down the partition function. It's e to the minus beta G mu B, expectation of B effective, times plus 1/2 plus e to the plus G mu B, beta G mu B, expectation B effective, times 1/2. I hope this looks familiar. Then we can differentiate this partition function in order to get expectation of sigma I. And the expectation of sigma I then becomes minus 1/2 hyperbolic tangent of beta G mu B, expectation of B effective, times 1/2. Okay? So now we have an expression for sigma I, for the expectation of sigma I, in terms of the external, the effective magnetic field, the temperature, and G mu B. So far, so good? Happy with this? All right, good. So now the last step is we have to figure out what this expectation of B effective is. Okay, so expectation of, I'll write this way, G mu B, expectation of B effective is just G mu B, B, the external magnetic field, minus J sum over J is neighbor of I, times expectation of sigma J. Okay, so I just took the average of B effective here. And the final step of the mean field theory is that at the end of the day, all sites should look the same. So the average of sigma on site I should be the same as the average of, so this is step 2, self-consistency. Average of sigma on site I should be the same as the average of sigma on site J. There's nothing special about site I versus site J, and we'll just call it sigma. Okay? So we're just setting the average of sigma the same on every site. So if we do that, then our equation here with the tangent, the hyperbolic tangent, can be written as sigma equals minus 1/2 hyperbolic tangent. And now I'll plug in our expression for B effective, where, well, actually, all right, well, okay. Up here, this sum here, I suppose, this sum here can be Z times sigma, where Z is the number of neighbors. Sorry, number of neighbors. Since we set sigma, expectation of sigma J to be just this number sigma, and there's J terms in the sum, Z terms in the sum. Is that clear what I just did? Sorry, it was a little messy. Okay. All right, so this ends up coming out tangent of minus beta J Z over 2 times sigma plus beta G mu B B over 2. So this is just a rewriting of the equation up there with the hyperbolic tangent. I plugged in B effective, and I plugged in J times Z for where I had J times expectation. J times Z times sigma is where I had J times sum over neighbors times expectation of sigma J. Good? Yes? Good? All right. All right. All right. So this is our final result. And it's some sort of self-consistent equation for the magnitude of sigma, which is the expectation of the spin on site I. And so in principle, we now have our solution for what sigma is as a function of the temperature, the coupling to the neighbors, the number of neighbors, external magnetic field. Okay? It's a complicated equation, but at least in principle we could solve it. The moment per site would then be minus G mu B times sigma, where the sign, so okay, this is the moment per spin. This minus sign comes from the fact that electrons have negative charge, so the magnetic moment points in the opposite direction of the spin. Okay? So in principle, we've now solved our problem. However, this is sort of a complicated transcendental equation, and it's not so obvious what its solution is. It's some equation for sigma, so we have to figure out how to solve it. And let's simplify to an easy case first. So case 1, or just set the case to b equals 0. External magnetic field is 0, in which case, simplifying this equation, moving a sign inside, we get sigma is 1/2 hyperbolic tangent of beta jz sigma over 2. Good? Still a hard equation to solve because it's still a transcendental equation for sigma. But there's a nice graphical way to solve this equation, which is to plot y equals sigma and y equals 1/2 tanh of beta jz sigma over 2 on the same plot. And where they intersect is the solution of this equation. Okay, so that's what we're going to do. That's how we're going to solve this equation. Is everyone still with me? Everyone happy? Yeah? Okay, good. So, so here we go. First, we have to decide. Put it over here. No, okay, let's right here. Y sigma over here. Sigma. Right, sigma over here. Then we'll plot the first curve, which is y equals sigma, like this. Y equals sigma. Okay, that's the first curve that we want to plot. And then the second curve is this hyperbolic tangent, which asymptotes at 1/2 and at -1/2. So it will asymptote here, and it will asymptote down here. But there's two possibilities as to what this plot looks like, what the hyperbolic tangent, what this hyperbolic tangent looks like. One possibility is what occurs for low temperature. Low temperature. What happens? No, sorry, let's do high temperature first. High temperature. High temperature is the first possibility. So at high temperature, beta is small, and so the tanh is a very gentle function. So it looks kind of like this. Okay, so this is high temperature. High temperature. Good? People happy with that? That's a hyperbolic tangent curve, and it asymptotes to this dotted line. So what we see is these two curves, the hyperbolic tangent and the y equals sigma curve, intersect only at one point at sigma equals 0. So the only solution is sigma equals 0. And that tells us that you don't have ferromagnetism at high temperature. You, in fact, get magnetization equals 0, or paramagnetism rather than ferromagnetism. Paramagnetism. Not ferromagnetism at high temperature. At high temperature. And this is actually quite typical, that any ferromagnet, if you raise it in temperature, at some point the ferromagnetism will go away, and you have this sort of intuition that what that's coming from is that the moments are fluctuating thermally around so much that they eventually stop pointing in any particular direction, and they don't point in any, if they're not pointing in any particular direction, it's not a ferromagnet anymore, and in fact it will be a paramagnet, as we'll show in a few moments. Okay? Now the other possibility is that we're at low temperature, so let's think about that possibility. Low temperature. In which case, the hyperbolic tangent is a much steeper curve, like this, because the argument of the hyperbolic tangent is larger, because beta is larger at low temperature. And so, in fact, there's three solutions. So this is the low temperature curve, low temperature. So we have a solution here. We'll call that sigma naught of t. There's a solution at 0, and then there's a solution here, which we'll call minus sigma naught of t. So we get three solutions, which are sigma equals 0, and then plus or minus sigma naught of t, which are non-zero. The fact that we have non-zero solutions for sigma is telling us that we have a ferromagnet, and naturally the ferromagnet can have its spins pointing up, or it can have its spins pointing down. So these are the ferromagnetic solutions. And this is not surprising because we know that if you go down to 0 temperature, this curve will be extremely steep. It will intersect right here, as a matter of fact, and you'll get complete polarization that sigma, the expectation of sigma is 1/2, meaning all the spins pointing in exactly the same direction. Okay, so that would be what you get at 0 temperature. At higher temperature, the intersection moves down to a slightly lower point, and you get slightly smaller sigma naught of T. So you get slightly smaller magnetization, but not 0 magnetization. Now, we might wonder, what about this guy here? We have another solution which tells us we have an expectation of sigma being 0. And this one actually is a little puzzling. It turns out it's not a physical solution, not physical. And you'll actually show that for one of your homework assignments. So it turns out what you'll show for your homework is that this self-consistent equation that we solve is actually the same thing as extremizing a free energy. And as you know, when you extremize something, you can either get a maximum or a minimum. So we're getting one maximum and two minima of the free energies. The minimum of the free energies are the things that are realized physically, and the maximum of the free energy is sort of a mistake. It comes out of the equations, but it's not physical. Okay? And it's much clearer when you actually write down the free energy, which you'll do for homework, and you'll see why it is that we don't keep that solution. So this one we sort of ignore, and we only keep track of these ferromagnetic solutions. Okay? So we'd like to know at what temperature do we go from being a paramagnet to being a ferromagnet. So let's write that down. At what T do we get ferromagnetism? Well, there's actually a name for that. Tc is known as, for T less than Tc, you get ferromagnetism, ferromag. And Tc is known as the Curie temperature, Curie temp, or the critical temperature, or critical temp, below which you have ferromagnetism. So we'd like to know, when do we get, what is Tc, or when do we get this ferromagnetism, at below what temperature? Well, the way to see that, again looking graphically, is to realize that the transition between having one solution and having three solutions occurs when the hyperbolic tangent, the function, is exactly tangent to the y equals sigma line, where it lines up just exactly with the same slope. And the reason that that's the important point where you have the transition from paramagnetism to ferromagnetism is because if the hyperbolic tangent were any less steep, you'd have only one solution, and if it were any more steep, you'd have three solutions. So we have to look for the situation where the hyperbolic tangent has exactly the same slope as y equals sigma. Okay? So Tc from finding slope of tangent of tang equals 1. So if we just expand the y equals tang equation here, the slope of tang, which we're setting equal to 1, is beta jz over 4. Or just rearranging a little bit, we get kb Tc equals jz over 4, which is the critical value of the temperature. Okay, is everyone still with me? Fairly happy? No? Yes? Maybe? Okay. Maybe. All right. So let me just pause for a second to sort of. Okay. Well, it's time for chocolate, actually. So, so for one chocolate bar, what's the critical importance of Jz? Think outside the box. Oh, it's really good. Who said that? I was going to say he was married to Beyonce, but it's close enough. Yeah. So, yeah. Very good. Yeah. Okay. No, Jay-Z is, besides being married to Beyonce, the importance of Jay-Z here is that it's, in fact, it's telling you that, okay, mother, does anyone know Beyonce's middle name? Do you know? No, that's her last name. No, that's her sister's name. Yeah. Come on, no one know. Does anyone know Beyonce's baby's name? Yeah, someone got it over there. Yes, yeah. Okay, I have one for you also. All right. Okay. So, those, okay. The importance of Jz here is actually it's the total amount of energy of coupling of the spin to its neighbors. And so we have Z neighbors here, and J is the amount of the coupling strength from the spin to each of its neighbors. So when the temperature gets above the total amount of coupling strength to its neighbors, the fluctuation in the thermal fluctuations of that spin sort of overwhelm the amount that it wants to stay in the same direction as its neighbors, which is what's keeping it a ferromagnet. It wants to have the same direction as its neighbors, and when the thermal energy is just greater than the energy holding it in place, you lose ferromagnetism. Okay, that's the intuition behind this picture here. All right. All right. Anyway, so at least graphically, we can take this picture and we can solve for sigma as a function of t. We just have to figure out where those two curves cross as we change t. And we'll get a picture that looks kind of like this. Here's temperature. Here's sigma. At 0 temperature, sigma is actually a half because all the spins are aligned. And then at Tc, it goes to 0. And above Tc, it's exactly 0. But then it comes down kind of like this at finite temperature as you change T. So this actually gives you the equation of state of how much magnetization you get as a function of temperature. And you can get it from this mean field approximation. It's not exact, but it's fairly good. Okay? All right, so the last step is that I promised you that up in this region here, we have a paramagnet. So we should actually convince ourselves that it really is a paramagnet, and one way to do that is to calculate susceptibility. So things that we know is up in this region, if you don't apply a magnetic field, sigma is 0. If you apply a small magnetic field, then sigma is probably going to be close to 0. So what we can do is we can take our original self-consistency equation and we can expand it for a small argument of the hyperbolic tangent, because everything inside there is, by definition, small. So either sigma is small or b is small. Everything is small. So we can write sigma equals, actually just writing this all out, I'm going to absorb a couple of minus signs here. Beta j c sigma over 2 minus beta g mu b over 2 magnetic field. Okay? And then we just rearrange this so we solve for sigma as a function of magnetic field. We get sigma, actually I'll write it this way, 1 minus jz over 4 beta equals minus beta g mu b over 4 times the magnetic field. And this, notice this quantity here is actually Tc, is kBTc. So with a little bit more rearranging, we get sigma equals minus 1/4 g mu b magnetic field b divided by kBt minus kBTc. And then we want to actually convert this into some sort of susceptibility. So the magnetic moment is minus g mu b sigma, and the magnetization, so this is a moment per site. The magnetization is the moment per site times rho, the density of spins. Density of spins. And then the susceptibility will be mu naught by definition dm dB at b equals 0, which just plugging in a couple lines up here, we then get 1/4 rho g mu b squared mu naught over kBt times 1 over 1 minus Tc over T. And this whole quantity here is actually the Curie susceptibility, Curie, for a spin 1/2. In other words, it's the susceptibility we would have calculated with just a free spin 1/2. In fact, it is exactly what we calculated when we calculated the magnetic susceptibility of a spin 1/2 in the last lecture. But then this whole thing gets multiplied by 1 over 1 minus Tc over T. So the susceptibility of our paramagnet above Tc is a susceptibility of just a system of free spin 1/2s, which aren't coupled to each other. And the effect of the coupling in the Ising model, at least within mean field theory, is to multiply it by this factor of 1 minus Tc over T. Okay? Now, you may notice that at the critical temperature, or the Curie temperature, this factor diverges. And that actually is physical. It's real. And the reason it's there is because we have to remember that the susceptibility tells you how much magnetization you get when you turn on a little bit of magnetic field by its definition. But when you go below the critical temperature, you get magnetization even for zero magnetic field. So the susceptibility must have gotten infinite somewhere along on the line. So that's what this term is doing there. Okay? All right. So this is the general scheme of mean field theory and how it works. Mean field theory, where was it? Yeah, mean field theory, and how it works, where we generally approximate some operator by an average. And this technique of mean field theory can be used much, much more generally than what we did here. For homework, you'll do a mean field theory calculation for an antiferromagnet as well. You could do it for a ferrimagnet. You could do it for spins that aren't spin 1/2. The fact that we got a hyperbolic tangent in this whole story came from the fact that we were thinking about a spin 1/2, so it had only spin up and spin down. If we were thinking about spin 1, we would have spin SZ equals 1, SZ equals 0, SZ equals -1. We'd get something more complicated than a hyperbolic tangent. We'd get a so-called Brouillon function. But the general themes of how you approach it, treat one piece of the system exactly and then insist on self-consistency, that remains the same. And the technique is used outside of magnetism in condensed matter. It's used for understanding liquid crystals. It's used for understanding fluid dynamics. It's used in astrophysics. It's used in atmospheric physics. Mean field theory is just a very general technique that's used for many, many things. And it's good to internalize the ideas of it. All right. We're going to use mean field theory for one more thing, which is to understand itinerant ferromagnetism. Itinerant, which is the next subject, itinerant magnetism. And the word itinerant means wandering, basically, or sometimes it means lost. But what it really means is that the magnetic moments are carried by mobile electrons, by mobile electrons. Now, since we started talking about magnetism a couple lectures ago, we thought about putting magnetic moments on sites, and the magnetic moments could move and point in different directions, but we didn't consider the possibility that the moments could actually hop from one site to another site. But in real magnets, like in iron, for example, it's quite typical that the same things that are giving you magnetization, these electrons, are actually moving around, too, in bands, and yet they manage to give us ferromagnetism. So as with other types of magnetism, itinerant magnetism is driven by interactions. It comes from the interaction between electrons, from interactions. So somehow we have to introduce interactions and treat them at least within some mean field approximation in order to understand itinerant magnetism. Now, of course, once you start introducing interactions between electrons, things get complicated very quickly. So we need a very simplified model which will represent the interaction between electrons and still give us the right physics. So the model we're going to use is the so-called Hubbard model. Hubbard wrote this down in 1963 to try to understand itinerant magnetism. And since he wrote this down, the Hubbard model has taken on a huge life of its own. It is probably the most important model of interacting electrons in all of physics. There have been probably, without exaggeration, 100,000 papers written on the subject of the Hubbard model. It's that important to the field. And the reason it's so important is because it's exceptionally simple, and yet its physics is quite complex. So, but the way Hubbard treated it in mean field theory is what we're going to do here. It's fairly simple. You get out a good result, which helps you understand itinerant ferromagnetism, which is what we're going to do. In the model, it's pretty straightforward. What we do is we start by writing a Hamiltonian that is tight binding electrons with hopping, with some hopping T. And this part of the Hamiltonian, tight binding electrons with some hopping, we've solved this before. We looked at this earlier in the term. We got these cosine-shaped bands. You can fill up the cosine-shaped bands. If it's a half-filled band, you get a metal. If it's a full band, you get an insulator. But never in just this model here, with just tight binding electrons with hopping, would you ever get ferromagnetism. You would never get a situation, if you only have this tight binding structure, where you would ever have a different number of up moments from down moments. They would always come out even. So we have to add something to it, which is going to change the story. And what we're adding to it is the interaction term. Sum over all sites I, parameter u is greater than 0, times the number of electrons on site I we spin up, times the number of electrons on site I we spin down. So we can write this. This is number of electrons on site I with spin up, down, with down. OK. So what this is doing is it's just telling you that you get an energy penalty of U whenever two electrons sit on the same atom, on the same site. OK? And we've actually discussed this Hamiltonian before. We didn't use the word Hubbard model. But I'll remind you, when we talked about Mott insulators, we discussed a situation where the interaction between electrons was so strong that you could only put a single electron on a site. And then you can get a situation, if there's a single electron on a site, then everything gets frozen in a traffic jam because no one can hop to the neighboring site because there's already someone sitting there. And even though you have something that looks like it should be a half-filled band, you still have an insulator, known as a Mott insulator. So this is exactly the same physics. We're just going to allow ourselves to turn on and off that interaction U, make it as strong as we want or as weak as we want. OK? So not too complicated. It looks like a very simple model, but again, it's one of these models. It looks simple, but isn't. It's solvable in one dimension, and absolutely nothing is known about it, despite 100,000 papers written on it in higher dimensions. OK, maybe not absolutely nothing, but not as much as we would like, which is why people keep writing papers about it. OK, so how do we treat this? Well, first thing we're going to do is we're going to write this interaction term as in the following form. We'll write it as u over 4 n up plus n down minus u over 4 n up squared minus n up minus n down squared. So that's just an identity. That's easy. We haven't done anything different here. What we're going to do now is we're going to make the mean field approximation. Mean field, and mean field always somehow or other means take something's average where you're not allowed to. Do something that's incorrect by taking an average. And what we're going to do, which is not quite correct, is we're going to take an average of these terms. So we're going to take average of n up plus n down and square it minus u over 4, average of n up minus n down and square it. OK? So that's the mean field approximation, or it's one type of mean field approximation we're going to use, and we're going to see what it gives us. Well, first of all, this term here, average of n up plus n down, that's just the total density, total number of electrons, total density. And that's fixed, probably fixed at the beginning of the day by the conditions that you have. So that's just going to give, that first term is going to give us a constant. The interesting thing is this term here, that n up minus n down is actually the moment per site divided by the Bohr magneton, and then it gets squared. So minus u over 4 moment divided by the Bohr magneton square, right? Because the number of spin-ups minus spin-downs is the magnetic moment on the site. OK? So we can rewrite this interaction term as some constant, which we're not interested in, minus u over 4. And then I'm going to rewrite this moment as magnetization times the volume of the unit cell over mu b squared. So V equals volume of unit cell. And the reason I'm rewriting it that way is because I'd like to have this thing as a magnetization. And magnetization has dimensions of moment per unit volume. So I have to put in the volume of the unit cell to have the dimensions come out right. OK? And the thing to notice about this is that the energy, the interaction energy, gets smaller as the magnetization gets larger. Why is that? Well, the intuition for that actually comes from the Pauli exclusion principle. If all the spins were aligned, in other words, if the magnetization were maximum, then there would be no interaction energy whatsoever, because you can never have a situation where two electrons sat on the same site. And you only have to pay this energy penalty when there are two electrons on the same site. So if you polarize all your spins in the same direction, you get the minimum possible interaction energy. And that's why it is that if you increase the magnetization, you drop the interaction energy. Is that clear? Good? All right. So from this picture, it makes you think then, OK, once you turn on the interaction, all the spins want to align. But it's not so easy, because aligning the spins costs you kinetic energy. And you have to sort of let these two things fight it out with each other. So let's remind ourselves what happens to the kinetic energy as you change the magnetization of a system. Now, we studied this before. So if you recall, polyparamagnetism, which we did in the first week, polyparamag, we actually calculated, although maybe not in the same language. You'll recall we had the density of states of spin up versus energy, kind of looks like this. And then we had the density of states with spin down versus energy. Kind of looks exactly the same. And if there's no magnetization, you fill them both up to the same level. Does this sound familiar from polyparamagnetism? Now, if you want to make, those are supposed to look identical. If you want to have a non-zero magnetization, what you have to do is you have to take some of the spin downs and make them spin ups. So to do that, let's take a sliver of these spin downs, and we have to move them up to higher energy up here. So it costs you energy. So these were supposed to be aligned. Like that. So it costs you energy to have a non-zero magnetization. It costs you kinetic energy to have a non-zero magnetization. All right? So we save some interaction energy, but it costs kinetic energy. So we have to trade those off against each other. So in order to figure out how those are battle against each other, we have to figure out how much energy it actually costs you to have some non-zero magnetization. So let's do that. So first, we'll go back to the polyparamagnetic calculation. So we're going to set U equal to 0 for a second. So now we're back to non-interacting electrons. And I'm going to write the free energy as a function of magnetization per unit volume. And that will then be minus m dot b. I think everyone's probably will accept that there should be a term like that in the free energy, minus m dot b, that wants the magnetization to align with the external magnetic field. But then the second term is less obvious, but it takes the form m squared mu naught over 2 times the polyparamagnetic susceptibility. And I'll just remind you, we calculated this in the first week of the term, that chi poly is mu naught mu b squared times the density of states at the Fermi energy. Does that kind of sound familiar? OK. Now, why is it that I wrote down this complicated term here? Why do I think this is correct? Well, first of all, this is sort of a Taylor expansion in the magnetization. So this is linear in magnetization. This is quadratic in magnetization. In principle, there would be higher terms as well, which we're going to ignore because we're interested in small magnetizations in general. But why would I give it this term, mu naught over 2 chi poly? Well, it turns out that it actually has to have this form. And to see that it has to have this form, we know that the free energy should be minimized. So df dm has to equal 0. And that tells me that minus b plus m mu naught over chi poly has to equal 0. And if you just rearrange that, that tells me that the magnetization is chi poly over mu naught times the magnetic field, which is what defines chi poly. The definition of the Pauli susceptibility for our free electron gas is the magnetization should be chi poly times the magnetic field. So that tells me the free energy has to have that form that I just wrote down. Okay? It's a little bit of a trick. You could go through the agony of trying to actually calculate the magnetization, the energy as a function of magnetization. You get the same result you would discover. It has to come out this way. Okay? So then let's turn off, set the external field, set B equal to 0, and turn U on, U not equal to 0. And then the free energy we get is going to be a combination of the two terms that we just calculated. So free energy per volume is then, well, OK, we have this term here. I turned off B, so I just get m squared mu naught over 2 chi poly. But then also, just about to scroll off the top, there's minus u over 4 times, well, OK, v squared over mu b squared, up times, I'm going to get rid of a V. Magnetization squared. Okay, it was V squared, but now it's going to be V because I'm writing the free energy per unit volume, not the free energy in this case. Okay, so I dropped a factor of volume, so it's not V squared, it's just V. All right, so what this is, I guess, we can factor out the m. So we have m squared and then mu naught over 2 chi poly minus u over 4 v over mu b squared. And this tells us, and there will be higher terms too, terms which are quartic in magnetization and so forth, which are not interested in. But the key thing to realize here is if this thing in the brackets is less than 0, then the magnetization wants to be non-zero. Whereas if the thing in the brackets is greater than 0, then the magnetization wants to be 0. Okay? So the criterion, criterion for ferromagnetism, for ferro, which is known as the Stoner criterion, is that this mu naught over 2 chi poly minus u volume of the unit cell over 4 magneton squared should be less than 0. So when you turn on the interaction strength strong enough, then the interaction strength wins, and it wants to have the spins polarize. Whereas if the interaction is not strong enough, then in fact it's more beneficial to have an equal number of spin-ups and spin-downs because you save kinetic energy that way. Actually, we can rewrite this in just putting in the definition of chi poly, we can write this as volume of the unit cell times u times g at EF should be greater than 2. It's equivalent. Okay. So that's what we get out of this mean field approximation for figuring out when we have ferromagnetism. But one of the things that's interesting about the Hubbard model is you can also get Hubbard antiferromagnetism. Hubbard antiferromagnetism. Antiferromagnetism. And this occurs when we have U is large, U large, and 1 electron per site. So this is in the Mott insulator regime. Mott insulator. So if U is large, it prevents you from having 2 electrons per site, or mostly prevents that. And then since it's 1 electron per site, you have this traffic jam of electrons where you have exactly 1 electron on every site. And the way to convince yourself that this thing is going to be an antiferromagnet is to try the 2 possibilities. So case 1 is consider a ferromagnet. Case 1 is consider a ferromagnet. So we have a bunch of spins, electrons, each with their spins sitting on each site. They're all aligned. And the energy of this situation is actually 0. The energy of the ground state is exactly 0. And the reason it's 0 is, well, you never pay any interaction energy because due to the Pauli principle, no electrons sit on the same site ever. So you don't ever pay the Pauli price. You don't ever pay the U energy. And also, the electrons can't hop from one site to the other at all because they're in this traffic jam, so they can't hop. So the total energy of hopping is also 0. Now, the second possibility is that you have an antiferromagnet, case 2, antiferromagnet. And this is a little more complicated because we have spin up, spin down, spin up, spin down, and so forth. And here, well, an electron can hop to the neighboring site, but it has to pay a price to do so. So you'll get spin up, spin down, you'll have 0 on this site, and then you have up, down on this site, which costs you energy U, and then up on this site. So this is an excited state, which is a valid excited state. It costs you some energy U. U might be large, but at least virtually, you can make such a thing. And so in second-order perturbation theory, due to this sort of hopping process, you get a shift in the energy, which is sum over all possible excitations, excitation, hopping Hamiltonian, ground state, squared over energy 0 minus energy excited state, and this is less than 0. So in fact, the change in energy is less than 0. So antiferromagnetic energy for antiferromagnet is less than energy of a ferromagnet when you have 1 electron per site in this Mott insulator limit. Now, this might seem a little complicated, but let me rephrase what we just did. If you have a ferromagnet, so in the case of a ferromagnet, each electron is basically sitting in an infinitely tall well. You can't hop to the left, it can't hop to the right. That's absolutely forbidden by the Pauli exclusion principle. So you should think of it as an electron sitting in an infinitely tall well. Whereas for an antiferromagnet, you have an electron in a finite well. So the height of the well is only u. It can hop to the neighboring sites. It costs an energy u, but it can do it. It's not forbidden by Pauli. And the energy of the antiferromagnet with a finite barrier is lower than the energy of the ferromagnet with the infinite barrier. So the antiferromagnet is favored. So this is sort of one of the things that makes the antiferromagnetism it makes the Hubbard model quite interesting, that it can give you antiferromagnetism, it can give you ferromagnetism, it can give you lots of other physics as well, including superconductivity, charge density waves, and all sorts of other things, which is why there have been 100,000 papers written on this Hubbard model. You're not responsible for all of that, I promise. You're supposed to know something about itinerant ferromagnetism, but that's all. OK, so sit still. We're going to go over on this lecture because we actually have come to the end of the course. So I just want to wrap everything up. We're going to cancel tomorrow's lecture. This is actually on schedule. It's actually planned to be 21 lectures, but I leave an extra lecture in case of disasters or running behind. And we didn't run behind. We did everything exactly as planned. So we've actually finished the course more or less. A couple of sort of organizational comments before the closing remarks. First of all, obviously no lecture tomorrow. That's the first comment. The second comment is no one, or not no one, but very few people actually use the message board heavily this term. That's OK. I don't know why it is people didn't like it. That's fine. But this message board is still up and running. And I think as it gets closer to exams, people will get more enthusiastic about using it and asking questions. That's fine. That's what it's meant to be there for. So don't hesitate to use it. Ask questions to your heart's content. I will try to answer as many of them as I can as you revise for your exams. The other thing that I want to ask you to do is let me know what you want to have for the revision lectures. We have 2 revision lectures in the 4th week of Trinity term, and I'm always completely at a loss as to what the most useful thing to talk about is. If you think I should try to just give an overview, I can do that. If there are particular questions from previous year's exams that you want to go over, let me know. I'll try to assemble something that people will find useful. All right, so just a couple of closing ideas for the course. When we started 7.5 weeks ago, I promised that by the end of the course we'd actually know something more about the world around us, and I think we genuinely do. We know things like why diamond's transparent and why iron's a magnet, and why solids expand at higher temperature, and many, many more things, and some of them very esoteric and some of them less esoteric. Things like why quantum effects are important for heat capacity, or how a transistor works, and how you determine the crystal structure of a material with an X-ray. For those of you who go on in science, I hope this forms a good foundation for future learning and discovering more things along the same lines, or even in other fields. For those of you who don't go on into science, that's fine too. I hope it's at least been a good and entertaining exploration of the natural world, and I hope it leaves you with a better appreciation for the subject at the very least. I do realize that there's an awful lot of material in this course, and I apologize about that. It was more or less a fixed amount of material fixed by the exams, the exam committee, and the syllabus, so we don't really have that much freedom to remove material. So I realize that a lot of people view this as drinking from a fire hose. It's just so much information coming at you at the same time, it's hard to absorb. But ironically, the biggest problem with the course is that there's actually not enough in it. And I don't say that because I feel like you need to learn more for your exams. I say that because condensed matter is such an enormous subject that we've hardly scratched the surface. It seems such a shame to leave it here, but this is all we have time for. We could easily do a year of lectures or more on material physics or quantum effects or statistical effects or device physics or any one of a dozen types of things that we just barely mentioned at all, and as well as many, many things that we didn't even get to: superconductors, superfluids, fractionalized particles, so forth and so on. And I really hope many of you have the opportunity to go on and learn about those things in the future. And hopefully it will be as entertaining or even more entertaining as what you've learned so far. Finally, I just want to thank you all for having come to lectures and having looked enthusiastic throughout the term. Thank you very much.